Okay, let's start. Thanks for coming for the third meeting of Warsaw Quantum Computing Group. Today's lecture will be given by Michał Stęchły, the title Introduction to Programming Quantum Computers Using pyQuil. But before that, I will just say a few words of introduction. So as some of you remember, because I know that some of you also attended our first meeting, we started our meetings 2 months ago at the Faculty of Mathematics, Informatics and Mechanics of the University of Warsaw. And the last meeting was in December. The title of the lecture was Elements of Quantum Machine Learning. And it was the first meeting here in Przestrzeń from Facebook. So I heard that you like this place, so this is also one of the reasons why we meet here once again. And also, last time DaftCode became our sponsor. And also this time DaftCode again supports our event, so we are very happy that they support us. So as I said, lecture will be given by Michał, but before that I also would like to tell you about another interesting event that will be held here in Warsaw. It's a conference, Supercomputing Frontiers Europe, which is organized by Dr. Marek Michalewicz, and I also give a voice to Dr. Michalewicz, so he will invite you to this interesting event.
Thank you. Good evening, everybody. I wish to invite all of you and your friends and colleagues and students whom you know and work together to this conference. This will be the 5th edition of this conference. It started in 2015 in Singapore, ran for 3 editions in Singapore, and was moved to Warsaw. That will be 2nd edition in Warsaw. Just to whet your appetite, there will be a few very interesting speakers. Our keynote speakers will be Paul Messina from Argonne National Laboratories in Chicago, who is one of the leaders of exascale effort for Department of Energy in the USA. There will be Leon Chua, who is the creator of memristor. If you know from your physics, memristor is the 4th element of the electrical circuit, very interesting element upon which Stan Williams from HPE Labs created a memristor computer and is building that. There will be also the scientific director of NASA Labs talking about what NASA has in store in preparation for Mars landing and other things. So these are just 3 keynote speakers, but there will be many talks on artificial intelligence. There will be special tutorial on Thursday, 14th of March, given by people from D-Wave, and hands-on workshop on Friday, 15th of March. So you're all welcome. Tutorials and workshops are part of the conference. So there will be only 1 workshop on quantum computing, D-Wave. Thank you.
Thank you. Yes, so I forgot to put on slides information that it will be on from 11th to 14th of March. And here are some cards with QR codes if you are interested. And now I can just give voice to Michał. So Michał, thanks once again for coming, and the floor is yours.
Thank you. Okay, can you hear me? Okay, great. So, hop. Okay, so hello. My name is Michał, and today I would like to introduce you to programming quantum computers using pyQuil. So, first things first, I would like to introduce myself and my company. So I work for a company called Bohr Technology. We are a startup which is specializing in quantum algorithms. We are interested particularly in optimization, like in applications of quantum computing in optimization and machine learning. Yeah, we are doing many interesting projects. I can tell you more later, connected with optimization, logistics, and we also have a couple of open source repositories, so you can even check out our code. So about me, so I have some background in physics, in engineering, and in machine learning, data science. So I've done a little bit of quantum computing during my studies, and then I was interested in it, but it wasn't a very prospective topic because there wasn't any companies apart from D-Wave which were doing quantum computing. And then about a year and a half ago, I've heard about Rigetti Computing, a startup which is building a quantum computer. So I started being interested, and for the last year I'm doing some projects in quantum computing, and I'm mostly interested in like three things. So one is applications. So theory is useful, but it's not something I can spend hours and hours doing. Second thing is optimization problems, and the third is QML, which is quantum machine learning. So how to use quantum computers to enhance machine learning. Before working at Bohr, I worked at Estimode, which is a IoT startup from Krakow. And if you would like to stay in contact or learn more, I have a blog, mustythoughts.com. So today we are going to use a platform called Forest, or a language for quantum computers called pyQuil, by a company called Rigetti Computing. So Rigetti Computing is a Y Combinator startup founded in 2013, and they are building quantum computer which is based on superconducting qubits. There are many technologies with which you can build a quantum computer, and this is one of them. So they have many open source libraries for their computers, and Forest is like the whole platform for basically like everything you would like to do with them. Growth is a library of more advanced algorithms, and pyQuil is a language that we'll use. And actually, like Quil is like an assembly language for the quantum computers, and pyQuil is a Python wrapper that allows us to use Python to run the code on quantum computer. Okay, so I have a couple of assumptions when I will do this presentation. So the first is that you know Python, because we'll do live coding in Python. So if you don't know Python, then it's not that hard language, so I hope you will get along. You have some basic knowledge of quantum computing. You've heard it a couple of times. You know what like a quantum gate is, because I would like to focus on some practical aspects. This won't be like a theoretical talk. So I hope you've heard things like Hadamard gate, or I don't know, measurement, something like this. And basically the third assumption is that you've heard that the quantum computers are like probabilistic machines, and I won't explain exactly why and how this probability thing works. And before we go into the coding, I would like to ask a question about like you. So how many of you are would say you are writing software like on a daily basis, or programming, things like this? Okay, so how many of you are connected to academia, so either working at the university or students? Okay, how many of you are interested in things or have some experience with machine learning, data science, these kind of topics? Great. Okay, so I see like my audience is pretty well educated, and so I hope there will be nothing too hard in this short introduction. Okay, so I decided I will, since as I said, I will focus on the practical things, I decided to do a live coding session. So I will show you how to do everything with pyQuil, not everything, but how to start and how to do some interesting stuff. And from installation to some more advanced features of pyQuil. And I know there isn't like a lot of time, so since as I said, like I'm personally mostly interested with applications. So things like, so the fact that quantum computers nowadays are imperfect is something that is, you know, important for me. So since pyQuil allows us to like simulate the imperfections of quantum computing, this is something I would like to show you. And yeah, without further ado, let's go. Actually, like one more thing here. If you have any questions or something is not clear from what I say, please tell me. I will try to explain it better. One more thing. I've put this notebook on the repository board technology/training materials. So if you on GitHub, if you search for board technology, you will find this this notebook. So if you like to do everything at home again, then there's no problem with that. That's one thing, and the other is if you would like to code right now together with me, then also feel free to take your computer and do that. If not, it's also okay. Everything will be on the screen. Okay, so the first thing we'll do, since it's a Jupyter notebook, is this font big enough? Or actually, okay, at this point it doesn't matter. I will ask this again. So first thing is running a Jupyter notebook. So we've opened it, and I would like to open my notebook. Okay, so it works. So now there is a couple of things we would like to do before we start. Installations. So, well, you know, to actually use software from Rigetti Computing, you actually have to install it, which is pretty obvious, but and actually, fortunately, it is fairly easy to do that in basically do that. Actually, right now, I think it's not possible on Windows because they have not released their SDK for Windows yet, but they are working on this. But if you have Mac or Linux, it should work. So this, well, when you will, okay, let's do it. So first thing, do you know what a virtual env is in Python? Virtual environment. Okay. So in few words, it's like a sandbox. So you can use it to start with a clean environment for Python, and I really recommend doing it. So I will show you how to create it, and actually it's all written here. Hop, virtual hop, and we'll do Warsaw Quantum Computing Group. And it's doing something. Installing. Okay, now we are going to activate this virtual environment. Up, been activated. Okay, it's activated. So the next things we would like to use, since we are using a notebook, we would like to install, be able to use this environment in notebook. So to do that, we will write this command. Okay, and then we can create a kernel for notebook. Actually, since I've already done it, I won't do it again. And the next couple of things are very well described in the installation guide from Rigetti. So it's really simple. It's just a couple of comments. So here is the short version. So is this font big enough for guys in the back row? Yes, I will. Okay, is it now okay? Yeah, great. So one thing is you need to install pyQuil. Oh, sorry. Which is like pip install pyQuil, and that's all. Second is you need to download the Forest SDK. So basically you need to go to the main web page of Rigetti, and somewhere here, oh here, you need to put your email. Then they will send a like installation package on that email, and you have to install the Quantum Virtual Machine and Quantum Compiler, and that's basically all. And after you have done this, you need to have like 2 additional consoles. So in one, we will run qvm-s, which is like starts our Quantum Virtual Machine, and the other is QuIL c-s, which will start our QuIL compiler. So when we deal with programming a quantum computer, there are a couple of terms that are useful. One is quantum virtual machine. So it's basically like a simulator of a quantum computer. So we have to, in order to run our code on a quantum computer, we simulate it and then run code on that simulator. And the other thing is in this case is a compiler. So basically it compiles code from like what we have in pyQuil into the like assembly language for quantum computers. Another useful term is QPU. So it's quantum processing unit. So when we refer to QVM, it means simulation. When we refer to QPU, it means a real quantum hardware. Okay. Also in this tutorial, we need to install like a couple of other libraries, and then we're ready to go. So to like help with visualizing some concepts, I've written some functions for visualization, but they are not. If you would like, I can like go into details and go through the details and explain how they exactly works. But I don't think it's the most important thing here, and I don't know if we will have enough time. But basically, there are a couple of functions. One is plot state histogram. The other is basically plot quantum state. I will show how it works later. Okay, so now we are almost there. We can almost write our first quantum program. We have to, as usually in Python, we have to like import a couple of things. So first thing is program. So we would like to run a program on a quantum computer. So in order to do that, we need to import like a program object from program class from pyQuil. And another very useful command is get QC, which is like get quantum computer. The last thing we really need are gates. So as I hope you are aware, in quantum computing we use gates like X, Y, Hadamard, and others. And they are like similar to logic gates in regular computing. And one more thing that will be useful is a wave function simulator. Okay, so in quantum computing, what we do is we start from a quantum state where like all the qubits are 0, and then we perform some operations on this state, and then we get some other state in the end. And this state can be described as a wave function. And when we have a real hardware, we can't really like inspect how the wave function looks like, because when we start measuring it, the wave function collapses and, well, it's gone. But fortunately, when we use a simulator, we can, well, as the name of this function suggests, simulate a wave function. So then we have better knowledge and like better insight into what's going on with our quantum program. So it's it comes very, very handy in, like, especially in the like exploratory phase. Okay, so actually I have to perform that imports. And now, well, let's start with something easy, a program that doesn't do anything. So we firstly define our variable p, which stands for program. And we create an empty program. Then we need to like have a software, like, you know, Python representation of our quantum computer. So we run get quantum computer with some parameters. So we have quantum computer. So what we see here is actually pyQuil has really nice way to of defining a quantum computer. So this means that we created a 2-qubit quantum computer, which isn't a real device, but is a quantum virtual machine. So this way, we can like separate creating an algorithm, creating a program, and separate like on what device we would like to run it. So for example, we can, I don't know, do something like this and create, you know, a couple of different devices, each with like different parameters, and then use the same program and see how it behaves on different devices. Okay, and actually to run our program, there is very easy command, which is called run and measure. So what it does, well, it runs the programs, then measures what the output is, and it does it a couple of times. So it does it like 10 times. So let's see what's the result of such operation. Great. Okay, now it works. Okay, so what do we see here? So we see that for the qubit 0, we get an array of 10 zeros. So we did like 10 trials, and every time the output of our algorithm was 0. And for qubit 1, well, we also got like 10 zeros. So if we used different machine, we have 4 qubits, and so on and so on. So I hope at this point everything is clear. Yes? No one's lost yet? Great. So now we will have what we have here is a like helper function, which allows us to like visualize what's the output of the program better. So what it does, it just runs this runs our program several times, runs a wave function simulator, which is here, and prints a couple of things and a plot. So let's see how it looks like. Up. So right now, what we do here is we create a simple program where the only element is a Hadamard gate, which acting on a qubit 0, because that's the syntax we use in pyQuil for the quantum gates. And then we run and visualize program P on a 1-qubit machine and run like a simulation 100 times. Okay, so what we see here, okay, maybe do it this way. So we have an output which is either 0 or 1. So do you know what the Hadamard gate does? Nod or like shake your head, please. Okay, people are shaking heads. Great. So a Hadamard gate is a gate that allows us to create an equal superposition of state 0s and 1. So if we take a state 0, we apply Hadamard gate, and we have state which is equal superposition of 0 and 1, which means that if we measure it, there is equal probability that we will get state 0 or state 1. Is that clear for people who never heard about Hadamard gate earlier? Great. So when we inspect what's actually happening, we see, well, we actually got a bunch of zeros and a bunch of ones, and it's actually pretty lucky. We actually got 5 zeros, 1, 2, 3, 4, 5, and 5 ones. So we actually got from 10 trials an equal superposition, and that's actually a success. because if we do it like again, we can get something different. So like 6 ones and 4 zeros. So this is the part where this probability thing is like, we can see it working. So another output here is the wave function. So what you see here, it's notation used in like quantum physics in general, called bracket notation. So this means that we have a state of 0, a state of 1, and wave function like describes the whole state. So this number is probability amplitude, which has like some nice properties, but like if you are interested, and you should be, how it actually works, like you can read it by yourself. I don't want to like explain it in details here, but basically this probability amplitude is something that later translates into probabilities. So how we do that? We take I forgot like the name, but we don't square it, but we do conjugate square. Like we, how it's called? Sorry? Oh, thank you. Norm squared of this value, because you see here this is a real part and imaginary part. So if you like do a square of, you know, 1i times 1i, you get -1, and you know -1 it's not a good probability. So you take a norm squared. So multiply. I will write it down. Up. So it's like x time x star. Oh, okay. So x star is a conjugate of x. And if we do this operation, we get actually like the probability values. So this funny number here is actually 1 over square root of 2. So if we take 1 over square root of 2 and multiply it by conjugate of 1 over square root of 2, which is 1 over square root of 2, we get 2. Oh, sorry, half. Yeah. So actually the probability of getting this state is 0.5, and of getting the other state, so 1, is also 0.5. Okay, so we can run it several times, and you can see that, well, sometimes if you are unlucky, we'll get only 2 zeros and 8 ones, and so on and so on. So actually, to see that it really works, it's good to have like a huge number of trials. So we measure it as many times as we can to get as close to the real distribution as we can. Okay, so now something that might be sometimes useful is to create equal superposition of like all the states on a given number of qubits. So actually, since like pyQuil is a Python language library, it's fairly like easy to use some nice Python features like for loop to generate programs. So here we start with an empty program. Then we say that we want to run it on like 5 qubits, and for numbers from 0 to 4, we add to the program a Hadamard gate acting on qubit 0, 1, 2, 3, 4. And what's nice, we can use this syntax plus equal to like add this gate to our program. So it's like pretty concise notation. Then we can print out our program. It's sometimes useful to see like what the program actually is and run it. Okay, so as you can see, like the program we have is Hadamard acting on 0, Hadamard acting on 1, on 2, on 3, or 4. And we get some, like, some output. But actually this is more interesting, because what we see here is a wave function of, like wave function which represents an equal superposition of all the states for 5 qubits. And it's actually pretty hard to read. if we go like element by element, we see that every element has the same probability amplitude, which later translates to the fact that every element has same probability of, being measured. And if, like, to familiarize better with the bracket notation, this state means that we have, like, every qubit is 0. This means, and that might be tricky, that the 0 qubit is 1, first qubit is 0, third is 0, and so on and so on. And let's say, I don't know, this one means that the 0 qubit is 1, first is 0, and then we have 1s. So indexing is from right to left, and actually there is a reason for that, which you can read more. I've given a link to an article from Rigetti, which has this very catchy title, about like why they decided to use this kind of notation. So if someone would like to know more, there is a source for that. Okay, but what we got here? Well, we got something which frankly doesn't look at equal superposition of states at all. So we see that it clearly favorized state 11010 over, let's say, 10010. And, well, do you know why? Yes, because the number of trials is too little. So if we have actually 5 qubits, so 32 possible states, and we do 100 trials, then, well, it's obvious that we have to be really, really lucky to get equal superposition, like a nice, smooth distribution there. So if we have more, we see that, the differences are like a little bit better. If we get even more, yeah, it's like closer and closer to the uniform distribution, which is, well, this is actually an important feature of quantum computing, which I've like learned from my experience, like a little bit the hard way, because, well, if you just use not enough trials, then you can be misled into thinking that the program is doing something it's actually not doing, but you got some random, like, look, you actually, like, for example, got a result which had low probability of being there, but you were unlucky, and then you think, hey, something is wrong with my program, but actually it's not. It's just, well, bad luck, you can say. Okay. So the next thing is that you can actually construct it like this, so we can add multiple gates in like one line, or you can do the following: 0 p plus equals c naught 0 1, and this gives like the same output, which is actually a Bell state. So this is a state where we have equal, like, for example, for 2 qubits, like Bell states are only for 2 qubits. So for 2 qubits, we get either 0 0 or 1 1. So who is not familiar with a C-NOT gate? Okay. So what a C-NOT gate does, it's like controlled NOT. What does it mean? Ha! Great. So we have 2 qubits. Qubit 1, which is in state like alpha, and qubit B, which is in state beta. And at the end, what we get here is alpha, because this gate doesn't influence this qubit. And what we get here is either beta or minus beta. So what happens, as I said, it's called C-NOT for a reason, because it's controlled NOT, and NOT is like minus. So if alpha is equal to 0, so then then the other state doesn't change at all. And if alpha is equal to 1, then these states change to like beta to minus beta. Is this clear? Yes, okay, great. So basically, that's it. So what's happening here? Okay. I will write it on the whiteboard, it's easier. So what we do here is that we apply Hadamard gate and then CNOT gate. So we always start from state 0, 0. So Hadamard gate, what it does, it creates a state, as we already said, that has equal superposition of 0 and 1. So at this point in our circuit, we have this state. And actually, in the end, we also have the same state. But what happens here is that this qubit changes, like this, it doesn't change if this one is 0, but it does change if this one was 1. So in the end, we will get either state 0, 0, if like this one was 0, or 1, 1, if this one was 1. Because if this is 1, then this one flips to 1. This minus here, damn, it doesn't make sense. Sorry. So actually, yeah, like I've got confused. It's actually not minus beta, it's 1 minus beta. Oh, this makes more sense. Because if it's 0, then this doesn't change. If this is 1, then if that was 0, it flips to 1, which is okay. 1 minus 0 is 1, so it flipped. And if that was 1, then it flips to 0. Is it clear? Sorry for the mistake, just like got confused. So what this, okay, so this is CNOT. So what this and actually this quantum circuit does, it creates a state where we have equal superposition of 0, 0 and 1, 1. And actually we need to add this to for this to be true. Okay? And what we can actually do, we can create a state called GHZ state, where we have an equal superposition of either having only zeros for n qubits or only ones for n qubits. So let's see. For 5 qubits, we got either ones for every qubit or zeros. And as you can see, this is exactly what I have written here. So 1 over square root of 2 of having like only zeros, only ones. And well, we also got the same result here. Okay, great. So is it clear for now? Is it all good? Okay, so let's go into the quantum gates in more details. One moment. Okay, we are ready. So right now we would like to see how each quantum gate affects like our qubit, basically. So again, whoa. Okay, everything okay? Okay. So we won't get into the nitty-gritty details of what actually every gate does, because this is something you can easily Google and go from math by yourself. We'll just like, I'll say like, show a couple of examples so that you have some basic ideas. But this is like, by no means I would like to learn you everything that there is about quantum gates. So let's start from something easy. There is something called identity gate. And, you know, which is not very surprising, what identity gate does, it does like nothing. So it doesn't change the state of qubit at all. So if we start from 0, we end up in 0. Yeah, so that was easy. Another gate which is used, we already actually talked about, is Hadamard gate. So we already talked about it. So I hope you all get how it works. But actually, it might be worth to explore something called a block sphere. So who knows what a block sphere? No, who doesn't know what a block sphere is? Okay, a couple of people. So a block sphere is, we'll start with identity. So a block sphere is a nice way of visualizing a single qubit and in what state it is. So we have 3 axes, which is x, y, and actual z. And when we are, so this nice green vector is a representation of a qubit. So if this vector points right here, we are in state 0, like simply 0. If it points here, we are in state 1. So if it points somewhere else, then we are in some different state. So since we know that actually Hadamard gates creates an equal superposition, then let's see what happens if we apply to the state, if we applied Hadamard gate. Up. So what happened is that we actually are in this state. So every state on the equator of the sphere represents an state which is an equal superposition of qubit being in 0 or 1. So actually, like, if you move this arrow, you know, on the like on the sphere, then the higher you are, the more probable it is that you will get a 0 in the measurement, and the lower you are, the less probable it is. I mean, the more probable is that you will get 1. And actually, what's interesting is that I said that like all the states on the equator gives us like the same superposition. So we'll get into like how it's exactly possible in one moment. So let's say we apply an X gate. So what an X gate did is it flipped our qubit from 0 to 1, as we can see. And if we rerun this, you can see that, yeah, it's actually like right now it's 1. So maybe Y gate. What it does, it flips our qubit from 0 to 1 too. But there is a slight difference. And the slight difference is here in the wave function. So this is actually something that's like, this makes one of the things that make quantum computers different and actually like much harder to understand than like a regular logic. So here we have this wave function and this probability amplitude, and we see that it's like probability amplitude of 1. So there, if we do this like norm square of 1, we get 1. So there's like probability of 100% of getting 1. But if we do Y, we get 1 J, but I prefer I notation. So 1I. So 1 imaginary unit. So if we do norm squared of this imaginary unit, we also get 1. So actually, even though these two states are different states, they, when we perform a measurement, they both collapse to qubit being like equal to 1. And actually, later on, I will show you an example where we explore how it can affect our algorithm. So there are also a couple of other gates. For example, RX gate. So this is rotation X, which means we rotate our state around the x-axis. So the first argument is angle, and the other is on what qubit we would like to perform this operation. So as you can see, we have this, after rotating by 1/4 of pi, we get a state like this. And as I said, well, the higher the arrow is, the more probable it is that we'll get 0. And actually, well, as you can see from these probabilities, it's, yeah, more probable that we'll get 0, and we got more zeros. So it works. Or, for example, something like this. And actually, as you can see, we rotated this vector, which was here, by 90 degrees around the x-axis. So we are here. And actually, this state is also a state where we have equal probabilities of getting either 0 or 1, but it's again a different state than what we got from Hadamard state and from Hadamard gate. And actually, we can run another rotation around y-axis, and we get another state, which is this. And same with our z, we can do a rotation, and we get another state, which actually looks exactly the same as our initial state, because the arrow is all up. But it's a different state, because we rotated this arrow around z-axis, like actually it was 90 degrees, so like this. And well, even though it looks the same when we measure it, it's a different quantum state. Okay, so now let's see it in action. Let's take okay, so maybe first, was that clear? Yes? Great. So let's start with well, Hadamard gate. And we know what Hadamard gate does. So that's great. And then, oh, I forgot about CNOT. No, I mentioned CNOT. Good. But I forgot to say what exactly this Python implementation of quantum computers does with CNOT. So we provide two integers here. One is the index of a control bit, so this one, and the other is an index of the qubit that we would like to act on, so this is 1. So if you want to perform CNOT between 0 and 1, we do something like this. Okay, so we do a CNOT, and now we have, as we discussed earlier, a nice Bell state, so either 1, 1 or 0, 0, which we got here. And then let's perform Hadamard gate on that state. Up. Okay, so actually, if we perform Hadamard on both 0 and 1, we get still a nice Bell state. So it's like everything is great. But what I would like to show you is that actually the phase matters, and this amplitude, the probability amplitudes really matter, because we started from a state like this, and we would like to visualize it. So we do it here, and yeah, that's it. So we measure either 0, 1 equal probability. But what if we start from this state here, which, as we said, is like it gives the same output, so either 0.5 or 0.5, like either 0 or 1, same probabilities. But as we can see, the vector is clearly in a different place. And we see that, well, it doesn't look like 1 over square root of 2. So if you run this whole algorithm, but from the initial state like this, what we get is we get an equal superposition of like all the states we have here. So 0, 0, 0, 1, 1, 0, 1, 1. But if we started from this, from the just using Hadamard gate, we get either 0, 0 or 1, 1. So even though it's really like because what's like intuitive for us humans is like this final number, probability, and we can actually understand what does it mean to get 0 with probability of 30% and 1 with probability of 70%. But it's very hard, at least for me. I mean, maybe some of you it's like much easier to visualize this like complex Hilbert space, but I think like for most people it's not intuitive, at least like in the beginning. What does it mean to have a state which has, you know, probability amplitudes of 0.5 minus 0.5 times I? And even though it's like hard to grasp, it's really important in quantum computing, because this is partly something, this is partly a place from which the power of quantum computing and what we can actually do with those qubits comes from. So that's why I wanted to show this example, that if we measure these two states, we would get, we can't distinguish them by only measuring them, but if we perform the same operations on one or the other, we get very, very different output. Okay, so is it clear? Should I like go back to something, repeat something? Any questions? Okay, great. So we can go further. Okay, so maybe also other thing. Am I going too slow? Who thinks it's too slow? Okay, who thinks it's too fast? Okay, so I guess for most people it's like right. So please let me know if I'm going either like, maybe I see like there's, yes? Mm-hmm.
So my question is that if that will be reproducible, because all the probabilities are taken from some seed. It's pseudo-random numbers in this in the emulator or simulator.
So
but then when you run it on quantum computer, it's not reproducible.
Yes, so that's a great point. So one thing, yes. So first thing, if we set some seed, and actually, honestly, I'm like not sure how to do that in pyQuil. I never needed that, but probably there is a way of like, you know, starting this quantum virtual machine with some seed. So then we can run our programs and get the same results every time we run it, because it's pseudo-random. It's not truly random. But if we run it on the actual real quantum chip, then this is a real randomness, and we have like physically there is like no possibility of being sure that we'll get the same output, like no matter like what we do with the system. And actually that's an interesting point, because one of the very well-known researchers and educators in quantum computing, Scott Aronson, he actually was testing, like he said that actually one of the very early applications of quantum computers might be being this like a generator of the really random numbers. So the one that you actually can't cheat, or you can't exploit the system, because this is really random thing. So that was one part, and the other is that yes, we run it like also something I would like to show is that we actually run it all on the simulator, and well, this simulator runs in this window. So actually, as you can see, we have logs, so we can see that okay, we are making a QVM of 2 qubits. We are doing like some computations on that, and well, it's nice to see that this is really going on our machine. Okay, so have I answered the question or forgot about something? Great, cool. Okay, so now actually, as you probably noticed, this measurement part is pretty important, because well, it does something with the state, and as I said, it collapses the wave function. So how it actually works? and what we can do with those measurements. So here, again, we create a simple quantum computer, 2-qubit QVM machine, simple program with one Hadamard gate, and we run it and look what we get. So we got something. But actually, as you can see, this is run and measure. But we can use a different method. We can use the method run. So, well, let's see what will happen if we use method run. And actually, I haven't tried it earlier, so I have no idea what will be the result. Up. But I'm really curious. No. Actually, user warning, you're running a QVM program with no measure instructions. So it will be always an empty array. So that's really nice in pyQuil that they actually warn you that you have done something wrong. But what if you wanted to use like a run method and don't run with measure? Well, we will see in a moment. Okay, so we again create a quantum computer. We create a program, we perform a Hadamard, we don't perform a Hadamard gate. Now we add a Hadamard gate to our program. And there is one more thing we need to do for measurements. We actually need to declare this classical register of bits. So this is called RO, which is readout for short. And we say that this will be a register of bits. And we say that this register has 16 bits. So it means that whatever, if we measure a qubit, the result of these measurements will end up in our quantum register. So we can add a measurement operation, which takes two arguments. One is 0, and the other is actual placed in this register, so 0. It actually makes sense to, put the output of the qubit 0 to register 0. And if we run it, we don't get any warnings. We get a nice 0. If we run it again, we get a nice 0, and again, a nice 1. So probably if we run it, enough number of times, we'll get a nice equal distribution of either 0 and 1s. But so what more we can do with that? So we can actually add another measurement, and we see that we got 2 bits. Yeah, because we measured qubit 0 and put the result in the register 0, and we measured qubit 1 and put it in register 1. And since we have not performed any operations on the qubit 1, we got 0, and we will always get 0. Okay, yeah. So what we can do now, we can as I said, the measurement collapses the wave function. It means that the quantum state that was there is totally gone, and what we have now is the state of qubit being either 0 and 1, and whatever beautiful set of imaginary numbers, complex numbers we had in this probability amplitude, now no one cares, it's gone. So actually it doesn't make any sense to perform any operations on a qubit after we measure this qubit. So we did X gate, which is flips 0 to 1 and 1 to 0. Measure it 100 of times, and that's the output. And if we now try to use a Hadamard gate after we measured it, well, we still get the same, because at this point that state was 1, and if we can affect this state in any way. So this seems trivial because, well, we know that we can't put anything after measurement because it doesn't make sense. But actually, when you start doing your own algorithms and you do a measurement on the wrong qubit because, well, you made a mistake, then the outputs of your algorithms are doesn't make any sense, and then you can see that actually you made a mistake and debug it. So it's just like a cautionary note to be careful what qubits you measure and when. And actually, in most cases, we don't need to do measurements by ourselves. So in most cases, you will probably want to use this run and measure function because it's like much more convenient. But there are some algorithms and like, you know, some places where you would actually like to do a measurement. But, well, I don't want to elaborate too much on that. Quantum teleportation is one such thing, so if you are curious, you can Google that. Oh, and one more thing. Actually, because what I did here is I put like a Python for loop, and well, it's not bad, but a little bit clumsy. So actually, it's nice that pyQuil provides us with this function, which is wrap in the numshot loop. So it tells us that we have to like perform this whole program like hundreds of times, and we get such output. And what's important, like good to know, is okay. So there are two things about pyQuil that you need to know if you want to do anything in pyQuil. So first thing is that this library, and honestly, like all the other quantum computing libraries I used, and I used a couple of them, they are, you know, being developed in like real time. So if you start the repository and see your GitHub feed, then you see that actually they push the commits like crazy. I mean, like tens of commits a day, for example, to given repository. So what it makes it like prone to bugs. So, well, actually, one thing is bugs, the other is inconsistency. So even though guys at Rigetti, at Xanadu, at IBM are doing their best to make these libraries easy to use, consistent, and bug-free, they sometimes fail. And for example, something like this, so you always need to check, like if, for example, you get array like this or another array like this, because it differs like from one library to another, and sometimes even in one library there are some inconsistencies in like what output you get. Okay, so actually we don't need that anymore. Cell clear. Okay. Okay, so is concept of measuring qubits clear? That's right. And do you need a short 5-minute break, or can I go further? Break is okay? Okay, so let's do a short break. Please maybe don't go outside, just like, you know, stand up, jump a little bit, and we'll come back in 5 minutes.
Yes, so please stay here in Przestrzeń from Facebook. Yes, there is a toilet, there is a kitchen, so you can take water or apple juice.
I think it's time to finish the break. I hope you are refreshed and ready to, you know, learn something more about quantum computers. So in this part, we will go more into the, I'll say that, like, what are like the problems with the real quantum computers and how we can use, how we can simulate this using pyQuil. Which is actually important because when it comes to applications, well, in order to get some, like, you know, benefits from using quantum computer, we would like to use a quantum computer and not the simulation. So this is one thing. The other thing is that actually one of the questions was like how many qubits we can simulate, and I think like for a regular computer it's around 30 something qubits. If not sure, like it depends on the computer, like what's the threshold, but then I think like above 40 qubits, to simulate more than 40 qubits you actually need a supercomputer, and anything above like 50 it's not really feasible. I've heard that someone devised like a new method of simulation where they can get up to 60, but well, basically on your computer using pyQuil it's about 30 something qubits. Okay, so one of the problems with a quantum computer, the real one, is that it's noisy. So if you perform, for example, some operation, you can't be really sure if this operation was really performed or if it has collapsed your state too early. So one thing is like noises associated with like gates. The other is, so it's called gate fidelity. The other is readout noise, like readout error. So you can sometimes actually read, so you measure the qubit and you get 1 instead of 0 or 0 instead of 1. This is like mostly associated with like the measurement system. And the third type of errors are decoherence errors. So these qubits can last only for a limited amount of time, and the longer the qubit exists, the more probability there is that this qubit will go to ground state, to 0. So, and actually like the quantum errors and quantum error correction is a very vast like topic, and like I'm no expert here. So if you would like to know more what errors actually there are different models of errors and so on and so on. There is a little bit more about it in pyQuil documentation, because you can simulate actually different models of errors. And like quantum error correction is like something you would like to search for. Okay, so let's see how the error actually works. So we have 2-qubit QVM, which is noisy. So this is one of the parameters you can pass to get QC. We create use Hadamard gate, and we should get something that's not an equal superposition. So as we can see, well, the probabilities are 0.5, 0.5. So that's not something we expected. But actually this, as you remember, is an output from the wave function simulator. So this shouldn't change if we use noise, because like the wave function, well, I don't know how to simulate like a wave function with noise, but this should change. So, but it doesn't really seem like it changed. And well, sorry, this is noise. No, actually, that's a good question. I haven't passed any noise parameters, and I don't have to, because it has some default parameters that I can use if noise is true. Okay, so actually, let's do something like Hadamard gate. Is actually, it's hard to say if there's noise or not, because it's like probability. So you have to really do a lot of measurements to see if the distribution is skewed or not. So let's do something simpler. So flip qubit from 0 to 1. Well, and we got only once here. It's like one, okay, so maybe 1 qubit QVM. Okay, so we got only once. So something is wrong. And actually, I was trying to see what's wrong. And there is another thing about, how to call that, there's another thing about pyQuil I love, and it's the community and the support from the Rigetti. So there is, so there is a Slack channel for users of the Rigetti computing, where like the members of the Rigetti, the employees, are very active, and other people are active too. So, so I've written on the Slack that, well, I was playing with the noisy QVM and it seemed it doesn't work. And I got an answer from Nicolas Tezak, who is one of the employees of Rigetti. Well, what should I do? So I should use measurements. And actually this was like half an hour after I posted it. Actually, the first answer was 1 minute after I posted it, but there was some, stupid mistake on my side. And later on, I got an answer from Matt Haringan, who is also from Rigetti. Like an hour later, he said that, well, it should work, but actually there is a bug that they already are aware of, and they already did a pull request to fix it, and in the next release this bug will be fixed. And actually, to go around this bug, you need to like specify these parameters separately. And yes, this is the PR from like which fixes this. And well, the workaround is simple, as I just can't do 1 qubit QVM. I have to pass SQVM like as a separate parameter, and then it should work. So what it shows a couple of things. So one is that, well, as I said, these libraries are really developed in real time and bugs happen. So if you spend 10 hours trying to get these things work and it should work but it doesn't, well, there might be some bug somewhere there, and it's better to ask instead of wasting your time. The other thing is that they are super helpful and they answer, like, they're in a different time zone, but they really answer your questions, and there are other people from all around the world that will answer your questions. It actually might turn out that if you ask something, it might be me, because I'm also on the Slack. And the third thing is that they really care and they really fix those bugs, and sometimes, well, you need to actually download the most recent, not released yet version to use some, you know, fixed like feature that has been fixed. And I think it's really good to know that, like, you know, before you start. Okay, so let's do it. And so we performed X gate, so we flipped 0 to 1. We did like thousands of measurements. It was noisy, and we summed like all the results, and it should be 1000 because, well, you know, it should be always good. But since it's a noisy simulation, then it turns out that actually we got it worked well only in 90% of cases. 91, 92, like something like this. And if we visualize it, then we can see that actually, since we are running on a 2-qubit machine, like the most probable thing that we will get is the thing that we wanted. So the first qubit is 1 and the other is 0. But sometimes the other qubit is also 1, because we got this readout error on the second qubit, and instead of reading that it's 0, it was 1. And also sometimes both are 0 because, well, the first one was not flipped and we read the other as 1. And, well, it turned out in this case there wasn't like 0-1 case, which is good. And it's important because using this, like using pyQuil, you can write code test it on a simulator, and then go deeper and deeper and deeper, and, you know, check how it actually will perform on the real device. So one like layer of being like of making a more realistic simulation is actually adding noise. Yes, this noise is some kind of pseudorandom, and probably there is some seed parameter somewhere, as like all this, the whole simulation is pseudorandom, but the real noise is like real noise. That's one thing. And the other thing that actually you can implement very like precise noise models of like what the chips they have at Rigetti, what kind of noise they really have. And I'm not sure how it works with Rigetti, but as far as I remember, like at some, I think at some point that even updated those noise models in the real time, so that you get like the real noise model of the chip like at the point like today and not yesterday. But I'm not sure, like 100% sure about it. Okay, so there is, this noise has some properties, because it's not like one noise, it's like at least these 3 kinds of noise I told you about. So the thing is that if we do a measurement of the uniform state, so, you know, 3 Hadamard gates on every qubit, like here, Hadamard 0, Hadamard 1, Hadamard 2, we get a distribution that is skewed. And it's skewed towards having all qubits in 0. And I actually ran it 10,000 times. So, you know, it shouldn't be that bad. And we can see that if I turn off the noise, well, it's pretty uniform, and we don't see any, you know, that 0, 0, 0 is any more often than the others. But if I add the noise, then we actually see this. And we see that 1, 1, 1 is actually, you know, the state that is the least frequent. And this is because some of the qubits that should be in this one, like in the cases where the state we would measure would be in 1, 1, 1, actually, I don't know, it took too long and it collapsed to 0, 0, 0, or like we got some readout noises. But in general, it's due to the due to noise, it's more probable that the state we'll measure will be like 0 than 1 if we do a Hadamard gate. And yeah, that's actually it. And I really recommend reading the docs of pyQuil, because it's like it's great source of knowledge about like how it actually works on one hand, and on the other hand about some cool features of what you can actually do with this platform. So here, if you are interested in like learning more about different noise models and seeing like what you can actually implement, well, there are a couple of functions like, I don't know, Krauss, dumping Krauss map, like whatever it means, you can learn about it from the docs. So the one problem with the quantum computers today is that they are noisy, and actually, you know, people at companies like IBM, Rigetti, they are working really hard to make them less noisy. But this is not the only obstacle that we face. So the other is connectivity. So in the ideal world, you could do, for example, a CNOT operation on every pair of qubits you would like to. But that was in the ideal world. In the real world, it depends on the, you know, actual topology of your computer. So there is a nice, which I found in documentation, function which is called list quantum computers. And if you run it, you can see what quantum computers you can use as your QC in getQC. So there are some Aspen chips, and this is some class of, well, architecture of from Rigetti, and you see that you have those Aspen chips with different number of qubits. You can also create a 9-qubit square, so, you know, which looks basically like this. And like you have nearest neighbors connections between qubits. And actually you can also create all kinds of fully connected topologies as we did earlier. So when we passed like one QVM, it created, you know, 1 qubit machine like simulator. If I created 5 qubits, then it was 5 qubits which were all connected together. Okay, so let's see what's happening here. Let's try to use this Aspen 2 qubits. Okay, so we failed. And as I said, well, you always have to check like what's happening and why it doesn't work. And actually in this case it doesn't work because we don't want to run it on the actual Aspen 1 like 2 qubit quantum processing unit QPU, but we want to run it on a quantum virtual machine. So we add SQVM parameter. And well, this time we got some error which says status. What does it mean? Ah, okay, so I forgot. So it's not only that we imported this QPU, we also perform operation X on qubit 0. So we want to flip qubit 0 from 0 to 1. And well, it's simple, it should work. I mean, I can't the only, you know, program that would be simpler would be doing nothing. So let's see, like identity gate well, it also doesn't work. So let's see, like maybe some other. This will work. Yay, it worked, but there was some other error. And actually, this was error from plot state histogram, which suggests that there is some bug in my function which I created earlier, but it worked earlier. So why there should be bug? Probably because the format of the output is a little bit different. Well, maybe it will work with this one. Not really. So we have this key error 2 here. As I said, you have to double check everything, and actually I could fix that because there's just like, you know, for this case the format is a little bit different and we should just fix one line, but I think right now we see that we got a state we wanted on this processor, and there is some problem with my code, not with the platform, so I will leave it as it is for now because we don't have that much time. And the fun thing is that we can actually visualize what chip do we have. So again, there's a little helper here. So if you would like to see like how actually this first, so Aspen 2 qubits chip look like, we would like to see this. Well, we run this function and it takes some time, and I have no idea why. But maybe, oh, okay. It actually, I have no idea. It's sometimes it works like a charm, sometimes it's take a lot of time to work. But actually, as you can see, we have two nodes. One is 14 and one is 15. And we have two edges, like one edge between 14 and 15. So, hey, we tried to perform 0, like X gate on 0 qubit, but it doesn't have a 0 qubit, so key error like suggests that. This error may be, oh, so some qubits were requested, but the QVM is limited to something else. So as we can see, we cannot perform operation on qubit 0 because there is no qubit 0. This first qubit we have is qubit 14. Why? I have no idea, but probably, well, this is some kind of way they enumerate the qubit on this particular chip, and actually to keep it like more realistic, they have not, you know, done reordering of the qubits. And if we run this other version, again we have nodes 14, 15, 16, and if we can run, I think it was, oh, nope, this. Whoa, that's nice. So we have something like this, and finally in this case we actually have a qubit 0, a qubit 1, but we don't have qubit 2, but we have qubit 3, 4, 5. And you can see what's the topology of this chip, and we can see like which nodes do we have. That's a great question, actually. So I have no idea why this is like particularly this topology they put here. I don't know. Maybe it's in docs. I haven't found it, but maybe there is like explained somewhere. But on the other hand, well, one thing is maybe they needed this kind of topology for some kind of experiments where you want to check something specific. So for example, for some quantum effects, you want to have this linear topology to just like, you know, check how qubits would work if you put them in line. For some other effects, you want to check, you know, for example, this square lattice. This might be one reason. The other reason might be that actually this is something that fits nicely on chip. So there are a lot of challenges in here. So like how to create a chip with given topology. So actually, I would say most common topologies on quantum chips, and this is overstatement because there aren't that many quantum chips, is something similar to this, so to square lattice or maybe like triangular lattice. So the earlier version of QPU from Rigetti, Acorn, it had like a triangular lattice. And the thing is that actually it turned out that, for example, one of the qubits was broken and you couldn't use it. So then you have this nice triangular lattice, but with one node. And for example, later it turns out that one of the connections is broken. So you have to, you know, take this connection out of the picture. And I suppose that after, you know, enough fabrication errors, you get some topology that doesn't look like anything reasonable, but actually that's due to fabrication errors and not because that was the design. But this actually is a good question because it shows you like how hard it is first to create a quantum computer that has some nice properties, and the other problem is that you actually, when you want to write a program for the real quantum computer, you actually has to take into account that you know, you don't have fully connected quantum machine. And why actually it matters that you don't have a fully connected quantum machine? Okay, so I would go, like, I don't want, you know, to make it too long. I will go very briefly. If you are interested, you can ask me afterwards about the details. But the thing is, if you create a 17-qubit quantum virtual machine and you run a nice program which is doing Hadamard on 0, and then you want to use CNOT on 0 and 14 and 0 and 1, you can actually print out the program. And what you see is not this Hadamard gate, and not CNOT gate, but, well, a bunch of other gates. Why is it? Because we don't have all the gates we use in theory implemented on the actual quantum computer. We only have a set of native gate sets. So basically, if you take those three gates, so RZ, Rx, and control Z, you can create any gate you want. Basically, you can like decompose any unitary, any gate you can use on quantum computer into some sequence of these gates with some parameters. So that's one thing. And actually, it's much easier to implement in hardware a limited number of gates than to implement all of them, because, well, I don't know that much about this hardware, but I can imagine that it must be really, really difficult thing to do. And I think they would rather focus on, you know, make it work as good as possible with these gates than, you know, giving us all the gates we want, but the gates that don't work at all. So actually, we have to compile our program, and this is why we needed to run this window, so Quill compiler. And what we see here is actually that Hadamard gate is compiled into a combination of the RZ and Rx gate, and CNOT is compiled to, well, it's not clear here, but to some other combination of gates. And, well, it's nice. And, okay, so instead of 3 gates, we got, well, a number of gates. You can actually see how many gates it is. The output is string, so we have to split it on the spaces. We get a list, and I think it was something like this. Okay, so here we have a list of all gates used. Yeah, I know it's a hack, but it works. And here we have how many gates we used. So 13 gates to perform 3 gates, really. So actually, it may turn out that you have this awesome, pretty quantum algorithm that you want to run on a chip, and it doesn't work. And you say, hey, but I used only 5 gates. And, well, no, not really, because after compilation, it's like 30 gates or whatever. And you thought that for 5 gates, the noise will not kill it, but it turns after you use like 30 gates, well, the noise is actually quite a lot. Actually, the number of gates we can use without the coherence killing our algorithm is more in like hundreds done in tens, but it's still like hundreds of gates is not that many operations we can perform on quantum computer. And what I wanted to show is that actually if you run it on this machine, which is 5 qubit, which has, well, let's see like what topology it has. So I think it was B here. So this is just linear topology, and it has actually qubit 0, 14, and 15. We see that, well, there are many more gates that we wanted. Actually 37 compared with 13. Why is this? Because we don't have, here we run CNOT on 0 and 14 and 0 and 1. We don't have actually connection from 0 to 14. To connect, to perform CNOT on 0 and 14, we have to go through qubit 1, qubit 16, qubit 15, and then qubit 14. So we had to perform this simple operation, we had to use qubit 0, 1, 16. Actually, it's interesting because we have not gone through 14 and 15. Why is it? Well, here we see something like pragma expected rewiring, which probably rewires the what order we do those computations, like in what order we treat qubits. And honestly, I'm not sure how it works exactly, but what I wanted to show you is to illustrate that, well, it's fun writing algorithms for quantum computers when you use quantum simulator, but when you start going deeper in layers, it starts getting really, really complicated. And actually, this is one of the reasons why, well, the progress of quantum computing, even though it's fast, it's not as fast as it could be, because there are things like this which can take you hours of debugging of why it happened. Okay, and again, there's some nice thing hierarchy of realism from pyQuil. One moment. As you can see, like, you start from the wave function simulator, and then you can go down into like layers of being more realistic down to the real device. Yes, question? Very, very good question. So is it possible to create your own topology and simulate it on like the topology you wanted? That's the question. Yes, you can find answer in the docs. So providing your own cheap topology, it's explained there, so I won't elaborate. I'm not sure about arbitrary gate. I think in the end, honestly, I don't know. Maybe you can pass some parameters to the Quill compiler that will allow you to like compile to different set of gates, but that's something you need to read in the docs to be sure. I just never tried using. In theory, you can do everything. With this particular piece of software, which is pyQuil, you have to read the docs. In theory, you can do all that computation on the paper, and it will work. So, okay, last thing. Okay. Okay, I will talk briefly. I don't want to like make it, make it too long. So I'll run this like super short. So another nice feature of pyQuil is that you can actually create parameterized gates. So if you have these rotations, you don't have to specify the angle of rotation at the moment of writing your code. You can say, I will have a theta parameter that I will specify later, and this will compile into the code, and then you can provide this parameter later. So this is nice. Sorry. Oh, that's 0. So this is nice, for example, for hybrid classical quantum algorithms, which I think we were talking about last time, a little bit at least. And we'll definitely come back to it at some point. And okay, as you can see, there is something different. Here we don't have a value, we have this theta. And actually, if we run this program like 200 times with different values of theta, then we can actually, we have like a bunch of different results, and these results, well, changes depending on actually what the value of theta is. Okay, and you can read more in the docs as usually. Last thing, so actually all that I said up to this point is, well, it's fun, but it's like not very practical. It's something for you to just like, you know, get acquainted with this platform and to see like what you can do and how you can, like, you know, try out your quantum algorithms using pyQuil. And here there is actually something that might be useful, and it's like very, very simple version of optimization the parameters for your quantum algorithm. And you can run it at home and go into details and see what exactly happens. If you have any questions, you can write me an email or re-get the Slack or whatever other channel you want. So this is a simple gradient descent algorithm that finds angle for the rotation x operation. So this is theta here, which will give us the probability, like the equal superposition. So if you run it, you can see that we have, like usually, many operations, and actually at some point we get like this value of theta, which was like seemingly good enough. And you can actually experiment with this by making more complicated algorithms, but introducing noise into the system and see how it changes. With noise, training will take more time. So this is like super simple example of some quantum machine learning or quantum optimization algorithm. And there are a couple of links. Some I would like to, briefly. Board technology is a link. Oh, it's a link to side of my company. I've recently created a tutorial on how to solve traveling salesman problem with actually pyQuil platform and QAOA algorithm. So if you'd like to learn more about using quant for optimization, I think it's a pretty good place to start. This was used by, I've created this in part using code from the tutorial by Mark and Thomas from Protein Cure. And there is a link. They did that tutorial on older version of pyQuil, so some things might not work, but if you would like to get some details, there are also slides and PDF with some more theory. This is really good place. If you would like to find some nice learning resources, Quantum Open Source Foundation is a good place. And also, we at BOR have this program called BQ Researcher Program, when we take people who are interested in quantum computing and would like to do a project in quantum computing, and we help them to actually do a project, do something that will be useful for other people, put it on GitHub, and, well, learn a lot about quantum. Also, a couple of articles, my YouTube playlist, where I put my favorite videos about quantum computing. And actually, it's 1 minute to 8 o'clock, so I think the timing is like not terribly bad. Thank you very much for listening, and, well, I would like, last but not least, thank organizers for inviting me for this event. Thank you. Yeah.
Okay. Thanks once again, Michał. Do we have time for questions?
Yes. Well, if someone would like to leave, then feel free to leave. If someone would like to listen to questions, well,
Okay.
ask me questions.
So the first question is, are there any questions from you? Yes.
Can you comment on this traveling salesman problem? So what is the quantum advantage that's expected in terms of complexity of this problem?
So actually, in this case, I don't know. Honestly, the thing is that QAOA is an algorithm for optimization using quantum computers, and it showed in the original paper by Fari et al. It showed that there is some advantage over some methods for solving a max cut problem. Actually, don't know what's like full mathematical theory in using it for traveling salesmen, but and of course it doesn't give any like immediate computational advantage right now, because the machines we have are like not that good and like too small. So that's a problem. But on the other hand, QAOA is in some sense similar to quantum annealing, and in quantum annealing you can get like the speed up from using quantum annealing comes from the fact that you can tunnel through very high barriers in the optimization space. So by analogy, if you run a problem using QAOA, it should also help you in these cases. But honestly, this is more for like researching it and seeing how it performs and what I can actually do, what kind of problems I can solve with quantum computers, because like this area is so unexplored and there are so many things we don't know that I think it's worth for the sake of just doing it. So I hope, well, I haven't answered your question like exactly, but I hope it satisfies. No, not really. Okay, we can talk about it later. Yeah, basically. I mean, maybe there is some theory that like says exactly what is advantage. No. Yeah, but it's not. Actually, there was one paper. No, there was one paper for TSP where they showed that actually in case of a type of graphs, you can use quantum computer to solve it with some speed up. It wasn't significant, but on the other hand, the algorithm they used was not taking into account any connectivity, noise issues, whatever, so it was purely theoretical. Sorry.
Okay, more questions?
In the first hour, you mentioned this problem that most people think in terms of numbers, and you have to the game rules of the game are specified in terms of complex numbers. Actually, I had a conversation with a leader of one of big companies in computer technology here in Warsaw, and he was insisting that, and he was right, that the great success of conventional computers is that you don't know anything about electronics to use them. And probably most of you just expect to have a user interface which would kind of allow you to specify a problem, and then you click the button, solve it in a quantum way, and it works. However, here is a significant difference, because this electronics still works on bits, but they play with them like numbers, adds them, multiplies them, etc., etc. And here the rules of the game are different. And so my question is whether a point of reflection perhaps, that maybe we are still in a very early stage of development of this technology, and if you want to make a contribution in computing, finally, you should rather insist of learning this perspective of kind of, you know, those arrows which were shown here, how it works and why it works. Because otherwise, I don't see how you can appreciate really the power of this technology. It's not like adding numbers, as it has been here demonstrated in many cases.
Yes, yes, I like totally agree with that. But there is like, I would say there's like, oh, sorry, another side here, and the thing is that people. So what this platform, what pyQuil allows you to do, is to actually, you know, play with it and see how it works, how it performs, even if you don't fully understand everything. And I've met some people who actually, when they approach it from the like only like theory side, and they try to understand it very, very well, like from the foundations, they actually at some point got discouraged because they couldn't grasp it as well as they would like to. But so for some people, this barrier is sometimes too high. And the thing is that if you can learn a theory and learn that, okay, there are this kind of like Pauli matrices and you can perform this kind of operations with them, then you can code it and see, okay, this happens here, this here, this here, this here, and like get some feeling of how it works, and then you can go back to theory and then go back to code. I think it's, I won't say like for everyone, but for some people, especially for people from a software background, I think this is more effective way, and like this actually this platform allows you to like make this learning more interactive. Yeah, or build teams. Yeah. Yeah, exactly.
Maybe you have also noticed that the Rigati provides a lot of manuals and how to do it. I mean, if I buy my laptop, it comes without manual. How to what happens on the main, you know, processor or something like that. So it is a unique moment to learn really how it works by studying those manuals, and to learn a lot about quantum computing by studying those manuals. But of course, that means that one should form teams of learners with various backgrounds, try to optimize progress, really. And I think we are here also to facilitate that, right?
Yeah, exactly.
I will be talking about it just in a couple of minutes. But now, any more questions?
I just want to ask, like, what's your board company is doing with this quantum computing? Like, what's you actually exploring?
So what are like the applications? So basically, companies are mainly like there are like the areas that quantum computing companies are exploring are, for example, optimization problems, because yeah, there are some reasons to believe that we can solve some optimization problems better. We don't have mathematical proofs for many of that, but still. The second is quantum machine learning. So there are some reasons to believe that actually we can enhance machine learning with quantum. And if you think about what are the applications of machine learning today, actually this means that you can actually enhance everything, but that's not like that easy. But let's say machine learning, simulations. So actually this is like this coming to this like original Feynman idea of like simulating quantum with quantum. So there is also a lot of research in maybe not a lot, but some companies are exploring like materials drugs discovery. Yeah, I would say like cryptography. Obviously, there is also some interest here. I think these are like the main areas, and actually like the businesses that are interested are, for example, like airlines, big pharma companies, financial sector. I mean, sorry, governments. Yeah, but there is huge potential, but well, we still have to wait a little bit to like see some real-world applications.
Okay.
Is there any chance for physical quantum chips to be like in in any perspective of time available to buy and within like
Right now.
Right now.
Right now, if you have $10 million, you can go to D-Wave, and which is like not exactly, but it's quantum annealer. But you can go to D-Wave and say, hey, give me your quantum annealer, and they will give it to you. Actually, IBM has announced like 2 weeks ago, 3 weeks ago, their new computer, which with 20 qubit chip with all the hardware needed to run it, and it's available on sale. I'm not sure if they yet disclose like what the price is and how it goes in details, but they announced it. And actually, if you have an idea how to do something interesting with quantum computer, you can ask Rigetti for access to their QPUs, and you can access that via like cloud API, so internet. IBM has small chip, I think 5 qubits, which is available like for everyone who will go to their site, get the API key, and just submit their quantum programs to this chip. But since it's the only chip available, like the queues are like really big and waiting times is huge. But you can actually run something on the quantum computer. So yeah, actually. How many people you know that have an actual supercomputer in the house? So there is actually how many people you know that would like to own a supercomputer because they need a supercomputer on a daily basis? I would say it's really hard. I don't think so. Maybe there will be some breakthrough technologies, but that will, you know, allow you to go so low with the cost, and that it will be possible. But well, I honestly not sure. But it's more like a question for like not in 1 decade. I would say like more in like 5 decades or 10 decades. So this is time scale here. I don't know that. Okay, so maybe you know, if you have any other questions, I think we can go somewhere and talk about it in like I'll say more relaxed atmosphere. Pavel suggested.
Yes, I would like to show a few slides. So indeed, there is, for example, Hala Koszyki very close. So you can go there together with you, Michał. Yes.
Yes. So if someone would like to talk,
time. Okay. So unfortunately I will have to leave, but I will just say a couple of closing words. Okay. Yeah. Thanks.
Oh, sorry.
Yeah, no problem. Okay, so yeah, I already mentioned about the Supercomputing Frontiers conference, which will be held in Warsaw in March. And a few people, even today, asked me about this quantum machine learning contest organized by Xanadu. So it's still possible to join. There are already 7 people in the team, and we already had 2 meetings. So we just started learning Penelane and Strawberry Fields platforms. And yeah, the competition will be open until the end of August, so there is still plenty of time to work on some interesting projects, interesting submissions. So if you want to learn this technology, which is advertised as the first programming framework for quantum machine learning, then feel free to contact me and join us. Yeah, so there are 3 tracks: educational award, software award, and research award. And yeah, so our meetings. So the next meeting will be in February. So Warsaw Quantum Computing Group will return, and the next lecture will be given by David. David, can you raise your hand? Okay, this is David, and David will give you a lecture which will be extension of the talk given by Michał, and it will be a lecture about Grover search algorithm, explanation, classical simulation with pyQuil. So it will be a bit probably more advanced stuff with pyQuil. Yeah, so we also hope that video recording from the meeting will be available on YouTube. We already have access to recording from the previous meeting, so I'm going to publish it on YouTube probably even this week. So I will let you know by email on our mailing list and on our Facebook group. So yeah, please follow our group. You can join our mailing list, and if you have any questions or feedback, then also feel free to contact me in my private email or official email of our group. So thank you once again for attention. Thanks, Michał, once again for a great talk. And yeah, let's stay in touch on Facebook and hope to see you next time in February. Thanks.